As we've discussed in the previous videos, the exact solutions that we currently have for the travel and salesman problem do not guarantee us any polynomial running time. So we currently do not have any algorithm that is guaranteed to produce an optimal solution in polynomial time, say in n squared or n cubed or even n to the power 100. Okay, so what we're going to do in this case is we're going to design an algorithm which is guaranteed to produce quickly a solution which is at least twice longer than an optimal one. Okay, such an algorithm is called two-approximate algorithm. Okay, so first of all, it is important to mention that our algorithm only works or only guarantees to find a solution which is at most twice as longer only for the metric version of the travel and salesman problem. So in this case, first of all, the graph is undirected, or the graph is symmetric, meaning that for any two vertices, for any two nodes, we have that the weight of the edge uv is equal to the weight of the edge vu. Okay, and also what is probably more important is that all the weights should satisfy the triangle inequality. Okay, so for any three nodes u, v and z, the weight of the edge uv is at most the sum of the edges uz and zv. So going from u to v through the node z could not be shorter than going directly from u to v. So in particular, the Euclidean TCP is also a metric TCP. Okay, so the Euclidean distances satisfy the triangle inequality. And what we're going to do for the metric, the TSP, is to design a very efficient algorithm that is going to produce a cycle quickly and is going to work even on instances in practice with millions of nodes, but the solution is not guaranteed to be optimal. At the same time, it is guaranteed to be at most 2 times longer than an optimal one. Okay, and this is once again called an approximation algorithm. Okay, so first of all, let me remind you that for a non-directed graph, we know that the weight of the minimum spanning tree is at most the length of the optimal travel and salesman person cycle in this graph. Okay, and this is true not only for metric graphs but for any graphs. And the reason is simple. If we consider an optimal cycle in this graph, it looks somehow like this, and then we remove some edge from this graph, for example this one, then what is left is actually some spanning tree in this graph. Why is it tree? Well, it is just a path, and the path is a special case of a tree. This is just a non-branching tree, right? This is some tree, and it is definitely, its weight is at least the weight of the minimum spanning tree. So the minimum spanning tree is the minimum one, right? So the weight of this path is at least the weight of the minimum spanning tree, which finally proves that the weight of the optimum cycle of a travel and salesman person in a graph is at least the minimum spanning tree. Okay, then we are ready to present an algorithm. So we first construct the minimum spanning tree of G. Recall that this can be done very efficiently in time, almost linear in the number of nodes and edges in the input graph. Okay, then we do the following strange trick. We double every edge in T and denote the resulting set of edges by D. Then what we see, and we will see this now on a small example, is that the resulting graph is Eulerian. So in this graph we can find an Eulerian cycle. Okay, this cycle visits all the edges that we currently have in our graph D. Then what we do is we just return a cycle that is obtained from the cycle found in D by removing all the repeated nodes. Okay, so let me explain all the details of this algorithm as usual on a toy example. So assume that we have several points on the plane, and the edges between these points are just distances between them on a plane. So this is definitely a metric case. Okay, so we first construct the minimum spanning tree. So in this particular case, it looks somehow like this, right? then we double every edge. So this is a very simple operation. So we just replace every edge with two copies of the same edge, and we assume that every such edge just has the same length, right? So they are shown like this only for visualizing that they are indeed double, right? And now what we see here is that the degree of every node here is even, right? Which means that the resulting graph is Eulerian. There is a cycle that visits every edge, not every node, but every edge exactly once. And we can easily find such a cycle. We can either construct an Eulerian cycle, and for these double trees, this is particularly easy actually, because we can kind of like hang it for some we can use one of the vertices as the root, and then we recursively first traverse one subtree, then the second subtree, then the third one, and so on. In any case, we can construct an Eulerian cycle in a graph somehow, and it can be done very efficiently. Let's consider one such cycle. So for example, we first go here, then here, then here, then here, here, and so on. So we finally traverse all the edges in our graph. And then we do a very simple operation. So we assume that we now need to transform the cycle into a cycle that visits every node exactly once. Okay, currently it visits some of the nodes more than once. Then we do the following. Let me use a different color for them. So we first go to this node, then we go to this node, following our Eulerian cycle, then we go to this node, then we go to this node. Then our Eulerian cycle, using the edge number 5, returns to this node that we already visited. So in order to bypass this, we do not return here, but we return to we go to the next vertex. So instead of going using edges 5 and 6, we go directly from here to here. And the nice property is that our graph is metric, which means that going directly from this node to this node can only shorten our current cycle. So using this edge instead of edges 5 and 6 can only decrease the length of our current cycle. And then we repeat doing the following thing. So we follow the edge 7, then we follow the edge 8, then we follow the edge 9, and then we need to and then our Eulerian cycle returns to a node that we visited already, then to this node, to that node, to that node. So we skip all these nodes and we return just directly to the initial node, right? So what we get as a result is a cycle like this one, okay? And we've almost proved already that this algorithm is too approximate. Let's now state this formally. So the algorithm is too approximate, and once again this means that it is guaranteed to return a solution which is at most twice longer than an optimal one. And it is also very efficient. It works in time almost linear in the size of our graph. Okay, because finding an Eulerian cycle can be done in linear time, and finding the minimum spanning tree can also be done almost in linear time. In time, something like E log V. Okay? So now let's prove. So we already know that the weight of the minimum spanning tree is at most the weight of the optimum solution, which means that when we double every edge of our graph, we get the set of edges whose total weight is at most 2 times optimum. Okay, and at the last stage, of our algorithm, we do some bypasses of our cycle. And since our instance is metric, we can only shorten the length of our cycle at this point. Okay, which finally proves that this algorithm is too approximate. Okay. Now, as a concluding remark, let me mention that this algorithm can be actually improved to give a guarantee of 1.5. This is known as a Christophidis algorithm. So in this algorithm, instead of doubling every edge, we actually find a perfect matching on edges of odd degree in this tree, and then we actually repeat the same procedure. Okay, so a better approximation factor is known. This factor is 1.5, and it is actually the best one. So it was It was presented by Christophidis in something like 77, so many years ago, and it has not been improved since then. Okay, let me also mention another interesting fact. So assuming that P is not equal to NP, assuming that for the general version of the travel and salesman person, there is no algorithm that guarantees an approximation alpha for any constant alpha, and even not constant alpha. So for the general version of TSP, we currently do not have any hopes for getting good approximations. Roughly this happens because if we had such an approximation algorithm, then we would be able to solve the Hamiltonian cycle problem also in polynomial time. But this would mean that P is equal to NP.